And now in this lecture we find out the area of the green semicircle using two different methods. In the drawing we have two semicircles. This is the white semicircle, this is the green semicircle. In addition, we know that line segment AC equals to 5 units in its length, line segment CB equals to 1 unit in its length. Our mission is to find out the area of this green semicircle. So we start with the first method and we join points P and B together by straight line. In the next step, I'll copy the white semicircle in a new page and we'll implement rule 7 on this white semicircle. So actually, this is the white semicircle that I go to the original drawing. AB is the diameter of this white semicircle, so I write it down. By joining points P and B together by a straight line, we created a peripheral angle APB. This peripheral angle APB is subtended on AB, this is the diameter of this white semicircle, therefore we can implement here rule 7. I repeat quickly on rule 7. According to rule 7, if a peripheral angle is subtended on the diameter of the circle, then it is equal to 90 degrees. So we have here a circle. AB is the diameter of this circle, and we have here peripheral angle ACB that is subtended on AB, that is the diameter of this circle, and therefore according to this rule, rule 7, peripheral angle ACB must be equal to 90 degrees in its size. Again, you can see here that peripheral angle ACB is a right angle. So whenever you have a peripheral angle that is subtended on the diameter of the circle, then it is equal to 90 degrees. You can implement rule 7 in our drawing. Why? Because in our drawing we have peripheral angle APB that is subtended on AB, the diameter of this white semicircle, therefore peripheral angle APB must be equal to 90 degrees in its size according to rule 7. Likewise, we join points P and C together by a straight line. In the next step, I'll copy this green semicircle in a new page and we will implement rule 7 on this green semicircle. This is the green semicircle that I covered on the original drawing. AP is of course the diameter of this green semicircle, so I'll write it down. AP is the diameter of this green semicircle. By joining points P and C together by a straight line, we created here peripheral angle ACP. This peripheral angle ACP is subtended on AP, the diameter of this green semicircle. Therefore, according to rule 7, peripheral angle ACP must be equal to 90 degrees in its size. So this peripheral angle ACP is a right angle, according to rule 7. This is angle A. Angle A is a common angle that belongs to both triangles. Angle A belongs to the green triangle APC, and angle A also belongs to triangle APB. So angle A is a common angle that belongs to both triangles. We'll define the size of this angle A as alpha. So this is the common angle, angle A, and it is equal to alpha according to definition in its size. So in this right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the green right triangle APC, this is the common angle A, that is equals to alpha according to our definition. This angle is the right angle according to rule 7. Therefore, this third recent angle must be equal to 90 degrees minus alpha. In the next step, I'll copy this green triangle, this green right triangle APC, and this right triangle APB in a new page, and we prove that those two right triangles, they are similar to each other according to angle similarity rule. So actually, those are the two right angles that I copied from the original drawing. In the next step, we prove that those two right angles are similar to each other. So we prove that this right angle APB is similar to this green triangle ABC. So why those two right angles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually, this is angle APB, the right triangle, and it is equal to this angle, that is actually angle ACP, the green triangle. Repeat again, angle APB in the right triangle equals to angle ACP in the green triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle, it belongs to both triangles. We have here angle alpha in this green triangle also. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to angle alpha as it is belongs to this white triangle, it will be defined as angle PAB. And it is equals to itself. So if we relate to angle alpha as it is belongs to this green triangle, it will be defined as angle PAC. Repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle PBA in the right angle. And it is equal to this angle, that is actually angle APC in the green triangle. Repeat again. Angle PBA in the right triangle equals to angle APC in the green triangle. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the triangles in this right triangle APB are correspondingly equal to all the triangles in this green triangle APC. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. So I can prove that the right triangle APB is similar, this is the sign of similar, to the green triangle APC. According to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB in this right triangle over side AP in this green triangle equals to side AB in this right triangle over side AC in this green triangle. Repeat again. We derive that side AB in the right triangle over side AP in the green triangle equals to side AP in the right triangle over side AC in the green triangle. What is the length of side AB? From the drawing, it is very easy to see that AB in total equals to 5 plus 1, that is 6. So we substitute AB by 6. and the length of the side AC is 5, so we'll substitute AC in the equation by 5. So in conclusion, we found out that 6 over AP equals to AP over 5. Here we cross multiply this equation, and we'll get that 5 times 6 is 30. So 30 equals to AP times AP, that is AP squared, or AP squared equals to 30. We take out of this equation, and finally we get that the means inside AP is equals to the square root of 30 units in its length. This is the means inside AP. That is equals to the square root of 30 units in its length. AP is the diameter of this green semicircle, and therefore the radius must be equal to half of it. So the radius R of this green semicircle must be equal to the diameter AP over 2. So the radius R of the green semicircle equals to AP, that is square root of 30 over 2. Again, the radius R equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. So the area of the green semicircle equals to the area of the circle, that is pi r square over 2. So I write it down. The area of the green semicircle equals to pi r square over 2. So it is pi r is equal to 30 over 2, therefore r square is equal to 30 over 2 square divided by 2. So the area of the green semicircle in total equals to pi times square root of 30 square is 30 over 2 square is 4 divided by 2. So the area of the green semicircle in total equals to pi times 30 over 4 over 2. 30 over 4 over 2 equals to 30 over 4 times 2. So here we have 30 over 2 is 15. So in total the value of this expression is 15 pi over 4. 15 over 4 is 3.75. Therefore in total the value of this expression is 3.75 pi. And 3.75 pi is equals to 11.78. In conclusion, we shall find out that the area of the green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. Repeat again. We actually found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, is equals to 11.78 square units. So we finished with the first method. In the next step, I will present to you how to find out the area of this green semicircle according to the second method. In the second method, we will join points P and B together by straight line. and I copy this white semicircle in a new page, and we'll implement rule 7 on this white semicircle exactly as we did in the first method. So actually, this is the white semicircle that I covered from the original drawing. We know that AB is the diameter of this semicircle, is the diameter of this white semicircle, so I'll write it down. AB is the diameter of this white semicircle. By joining points P and B together by a straight line, we get the peripheral angle APB. This is peripheral angle APB, and it is subtended on AB to the diameter of this white semicircle, and therefore, according to rule 7, peripheral angle APB must be equal to 90 degrees in its size. So this is a right angle according to rule 7. So peripheral angle APB is a right angle that is to say, line segment BP is perpendicular to line segment PA. Again, because of the fact that this is a right angle, it means that line segment BP is perpendicular to PA. PA is the diameter of this green semicircle. So we know that line segment BP is perpendicular to the diameter PA of this green semicircle. And here we also know that the center of any circle or semicircle is located on the diameter of the circle. So here this is point O, that is on the diameter AP, and point O is the center of this green semicircle. So point O is the center of the green semicircle, point P is the point on the green semicircle itself. Therefore, PO is the radius of this green semicircle. We define the radius PO of this green semicircle as R, therefore PO equals to R. So in conclusion, you can write down that line segment BP is perpendicular to the radius PO. Why? Because if line segment BP is perpendicular to the diameter PA, it must be also perpendicular to the radius PO. So line segment BP is perpendicular to the radius PO of this green semicircle, and therefore we can implement here rule 1. I repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. We have here a circle, and we have here the radius OM that is equals to R. According to rule 1, line segment AB is perpendicular to the radius MO. Okay? Or whenever you have a line segment that is perpendicular to the radius, like in this drawing, then that line segment AB is defined as a tangent to this circle. Okay, you can implement rule 1 in our drawing. Why? Because in our drawing we have line segment BP that is perpendicular to the radius PO of this green semicircle. Therefore, according to rule 1, line segment BP must be defined as a tangent to this circle. Why? Because it is perpendicular to the radius PO. So line segment PB is a tangent to this green semicircle, and the point of tendency is point P. Again, line segment BP is a tangent to this green semicircle at point B. And if you focus on this common point B, from this common point B, we have tangent BP to this green semicircle, and from the same common point B, if we draw a straight line towards this green semicircle, it will cut this green semicircle at point C and A. In this way, we get a chord CA. In conclusion, we found out that from the same common point B, we have tangent BP to this green semicircle, and we also have chord CA. Therefore, we can implement here rule 10. And please click on rule 10. According to rule 10 is true in any circle. So in any circle, if AB is a chord, you can see that AB is a chord of this circle, and PT is tangent to this circle at point T. PT is tangent to this circle at point T. Point T is the point of tendency. So from the same common point P, we have tangent AB. From the second common point P, we have chord AB of this circle, and we have tangent PT that is tangent to this circle at point T. So in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. We can definitely implement rule 10 in our drawing. Why? Because in our drawing, if you focus on this common point B, from this common point B, we have tangent BP, that is tangent to this green semicircle at point P, and we also have here chord CA. So all the requirements of rule 10 are satisfied, and therefore, according to rule 10, the following equation is true, that BP square equals to BC times BA. Again, BP square equals to BC times BA. So I write it down. BP square equals to BC times BA. Repeat again, according to rule 10, if you focus on this common point B, the following equation will be true, that BP square equals to BC times BA. BP is the missing side, so we leave it as it is. BP square equals to BC. BC is 1, so we substitute BC by 1. Times BA. BA in total equals to 5 plus 1, that is 6. So we substitute BA by 6. So in conclusion, according to rule 10, we found out actually that BP square equals to 6, 1 times 6, that is 6. So BP square equals to 6. We take a root out of this equation and find again that the missing tangent BP is equals to the square root of 6 units in its length. This is the missing tangent BP that is equals to the square root of 6 units in its length, so I write it down. In the next step, I'll copy the right triangle APB in a new page and we'll implement the Pythagoras theorem on this right triangle, triangle APB. PB equals to the square root of 6 units in its length. AB in total equals to 5 plus 1, that is 6. AB is the hypotenuse of this right triangle APB. And AP is the missing side. Here by PT is the equation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse on this right triangle APB is AB, therefore the square of the hypotenuse is AB squared, and it must be equal to AP squared plus PB squared. Repeat again. According to the Pythagoras theorem, in this right triangle APB, AB squared equals to AP squared plus BP squared. AB is 6, therefore AB squared is 6 squared, that is 36. So 36 equals to AP squared. AP is the missing side, so we leave it as it is. P squared plus PB squared. PB is square root of 6, therefore PB squared is square root of 6, square root of 6 squared, that is 6. So in conclusion, we shall find out that 36 equals to AP squared plus 6. We subtract 6 from this equation and find again that AP squared equals to 36 minus 6 is 30. AP squared equals to 30. We take out of this equation and finally get that the missing side AP equals to the square root of 30 units in its length. So actually, this is the missing side AP, and it is equals to the square root of 30 units in its length, so I'll write it down. AP is the diameter of this green semicircle, and it is equals to the square root of 30 units in its length. If the diameter AP of this green semicircle equals to the square root of 30, the radius must be equal to half of it. So the radius R of this green semicircle must be equal to the diameter AP over 2. AP is square root of 30, and square root of 30 over 2 is the radius R of the green semicircle. So the radius R of the green semicircle equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. So the area of the green semicircle is equals to pi r squared over 2. So the area of the green semicircle equals to pi. R is square root of 30 over 2, therefore r squared is square root of 30 over 2 squared divided by 2. So the area of the green semicircle equals to pi. Square root of 30 squared is 30 over 2 squared is 4 divided by 2. So the area of the green semicircle in total equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So 30 over 2 is 15. So in total, the value of this expression is 15 pi over 4. 15 over 4 is 3.75. Therefore, the value of this expression in total is 3.75 pi, and 3.75 pi is 11.78. So in conclusion, we have found out the area of the green semicircle is equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. So actually, in both methods, we found out actually that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, the area of this green semicircle equals to 11.78 square units. So we finish with the second method. In the next step, I will summarize the lecture. We'll start with the first method. In this lecture, we found out the area of this green semicircle using two different methods. So, in the drawing, we have two semicircles. Line segment AC equals to 5 units in its length, line segment CB equals to 1 unit in its length. Our mission is to find out the area of this green semicircle. So, we started with the first method, and we joined points P and B together by straight line, and I copied the white semicircle in a new page, and we implemented rule 7 in this white semicircle. So actually, this is the white semicircle that I copied from the original drawing. AB is of course the diameter of this white semicircle, and by joining points P and B together by straight line, we created a peripheral angle APB. Peripheral angle APB is subtended on AB, that is the diameter of this white semicircle, and therefore according to rule 7, peripheral angle APB must be equal to 90 degrees in its size. Likewise, we join points P and C together by straight line, and then I copied this green semicircle in a new page, and we implemented rule 7 on this green semicircle. This is the green semicircle that I copied from the original drawing. Here AP or PA is the diameter of this green semicircle, and by joining points P and C together by straight line, we created a peripheral angle ACP. Peripheral angle ACP is subtended on PA, that is the diameter of this green semicircle, and therefore according to rule 7, any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees in its size. Therefore, this peripheral angle ACP is a right angle. Okay. So, this is the original drawing. It's very easy to see that this is angle A, that is a common angle that belongs to both triangles, the green triangle APC, and this common angle A also belongs to triangle APB. So angle A is a common angle that belongs to both triangles. We define the size of this common angle A is alpha. So here this is the common angle A that is equals to alpha according to our definition. So in the right triangle APB, this angle equals to alpha. This angle equals to 90 degrees according to rule 7, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this right triangle APC, this is the common angle A that is equals to alpha according to our definition. This angle equals to 90 degrees according to rule 7. Therefore, this third missing angle must be equal to 90 degrees minus alpha. In the next step, I copied this green right triangle APC and this right triangle APB in a new page, and we proved that those two right triangles are similar to each other according to angle similarity rule. So those are the two right triangles that I copied from the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle, it belongs to both triangles. You can see here, angle alpha belongs also to this green triangle. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles, and finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I actually proved that all the triangles in this right triangle APB are correspondingly equal to all the triangles of this right triangle APC, therefore those two right triangles are similar to each other according to angle similarity rule. Repeat again, I actually proved that the right triangle APB is similar, this is the sign of similar, to the right triangle APC according to angle similarity rule. And for the fact that the two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side AB in this right triangle, or side AP in this green triangle, is equals to side AP in this right triangle, or side AC in this green triangle. Repeat again. We derive that side AB in the right triangle or side AP in the green triangle equals to side AP in the right triangle or side AC in the green triangle. AB is 5 plus 1, that is 6, and AC is 5. So we substitute AB by 6 and AC by 5, and found out actually that 6 over AP equals to AP over 5, because multiplied this equation, and finally found out that 5 times 6, that is 30, equals to AP times AP, that is AP squared. So AP squared equals to 30. We took out of this equation and finally found out that the missing side AP equals to the square root of 30 units in itself. This is the missing side AP that is equals to the square root of 30 units in itself. AP is the diameter of this green semicircle, and therefore the radius of this green semicircle must be equal to the diameter AP over 2. So the radius R of this green semicircle equals to the diameter AP over 2. AP is square root of 30, and square root of 30 over 2 is the radius of this green semicircle. So the radius of this green semicircle R equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of this green semicircle equals to the area of the circle, that is pi r square over 2. Repeat again, the area of this green semicircle equals to pi r square over 2. So it is pi r is equal to 30 over 2, therefore r square is equal to 30 over 2 square divided by 2. So the area of the green semicircle equals to pi, and square to 30 square is 30, over 2 square is 4, divided by 2. So in total, they have the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So in total, the value of this expression is 30 pi over 4 times 2. Here we have 30 over 2 is 15. So in total, the value of this expression is 15 pi over 4. 15 over 4 is 3.75. Therefore, in total, the value of this expression is 3.75 pi. And 3.75 pi is equals to 11.78. So in conclusion, we should have found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, this equals to 11.78 square units. We finished with the first method. In the next step, I presented to you how to find out the area of this green semicircle according to the second method. In the second method, we join points P and B together by straight line. Then I copied this white semicircle in a new page, and we implemented rule 7 in this white semicircle. So actually, this is the white semicircle that I copied from the original drawing. AB is of course the diameter of this semicircle. By joining points P and B together by straight line, we created a peripheral angle APB. Peripheral angle APB is subtended on AB, that is the diameter of this white semicircle. And therefore, according to rule 7, any peripheral angle that is subtended on the diameter of the semicircle of the circle must be equal to 90 degrees in its size. Therefore, peripheral angle APB is right angle according to rule 7. Okay. So here we have peripheral angle APB that equals to 90 degrees in its size according to rule 7. That is to say, line segment BP is perpendicular to PA. PA is the diameter of this green semicircle, so line segment BP is perpendicular to the diameter PA of this green semicircle. Where is the center of this green semicircle? The center must be located on the diameter PA, because any diameter must pass through the center of the circle. So this is point O, that is located on the diameter PA. So point O is the center of this green semicircle. Point P is the point on the green semicircle itself. Therefore, OP is the radius of this green semicircle. In conclusion, you can say that line segment BP is perpendicular to PA, so line segment BP must be also perpendicular to the radius PO. Why? Because if a line segment is perpendicular to another line segment, then that line segment must be also perpendicular to the part of the line segment. Line segment BP is perpendicular to the radius PA, therefore line segment BP is perpendicular to the diameter PA, therefore line segment BP must be also perpendicular to the radius PO. So line segment BP is perpendicular to the radius PO of this green semicircle, and whenever you have a line segment that is perpendicular to the radius of a circle, you can implement rule 1. I repeat quickly on rule 1. According to rule 1, the tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the domain we have a circle, OM is the radius of this circle, and this equals to R, and we have a line segment AB. Line segment AB is perpendicular to the radius MO. And whenever you have a radius that is whenever you have a line segment that is perpendicular to the radius, then that line segment is defined as a tangent. Here, AB is a tangent to this circle. Again, whenever you have a line segment that is perpendicular to the radius, then that line segment will be defined as a tangent to the circle. You can implement rule 1 in our drawing. Why? Because in our drawing we have a line segment BP that is perpendicular to the radius PO of this green semicircle. Therefore, line segment BP is defined as a tangent to this green semicircle. Actually, line segment BP is tangent to this green semicircle at point P. Okay. In addition, from the common standpoint point B, we have tangent BP to this semicircle. In addition, also if we draw a straight line towards this green semicircle, it will cut the green semicircle to point C and A. So from the same common standpoint point B, we also called CA. Again, from the common standpoint point B, we have tangent BP to this green semicircle, and we also have here called CA. Therefore, we can implement here rule 10. According to rule 10, rule 10 is true in any circle. AB is the chord of this circle. So from the common standpoint point B, we have chord AB. And from the same common standpoint point B, we have tangent PT that is tangent to this circle point T. So in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. You can definitely implement rule 10 in our drawing. Why? Because in our drawing, we have here, if you focus on this common standpoint point B, from this common standpoint point B, we have tangent BP that is tangent to this green semicircle at point P. In addition, from the same common standpoint point B, we have called CA. So all the requirements of rule 10 are satisfied, and according to rule 10, the following equation will be true, that BP square equals to BC times BA. Again, BP square equals to BC times BA. BP square equals to BC times BA according to rule 10. BP is the missing tangent, so limit as it is, so BP square equals to BC. BC is 1 times BA. BA is 5 plus 1, that is 6. Again, so BP square equals to BC, that is 1, times BA, that is 6. So BP square equals to 1 times 6, that is 6. So BP square equals to 6. We took out of this equation and finally found out that the missing tangent BP equals to the square root of 6 units in its length. This is the missing tangent BP. This equals to the square root of 6 units in its length. In the next step, I copied this right triangle APB in a new page and implemented the Pythagoras theorem on this right triangle APB. This is the right triangle APB, which I copied from the original drawing. We just right now found out that PB equals to the square root of 6 units in its length, and the hypotenuse AB is 6. AP is the only missing side. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle APB is AB, therefore the square of the hypotenuse is AB square, and it must be equal to AP square plus PP square, plus PB square. AB is 6, therefore AB square is 6 squared, that is 36, and it must be equal to AP square. AP is the missing side, so we limit as it is, plus PB square. PB is square root of 6, therefore PB square is square root of 6 squared, that is 6. So in total, we shall find out that 36 equals to AP square plus 6. We subtracted 6 from this equation and finally found out that AP square equals to 36 minus 6, that is 30. AP square equals to 30. We took out of this equation and finally found out that the missing side AP equals to the square root of 30 units in its length. Actually, this is the missing side AP, that is equals to the square root of 30 units in its length. AP is the diameter of this green semicircle. Therefore, the radius of this green semicircle must be equal to the diameter AP over 2. Repeat again, the radius of this green semicircle R must be equal to the diameter AP over 2. The diameter AP is square root of 30, so square root of 30 over 2 is the radius of this green semicircle. Again, the radius R of this green semicircle equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of this green semicircle must be equal to pi r square over 2. Repeat again, the area of the green semicircle equals to pi r square over 2. So it is pi r is equal to 30 over 2. Therefore, r square is equal to 30 over 2 square divided by 2. So the area of the green semicircle in total equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So in total, the value of this expression is equals to 30 pi over 4 times 2. 30 over 2 is 15, so in total, the value of this expression is 15 pi over 4. 15 over 4 is 3.75, therefore in total, the value of this expression is 3.75 pi, and 3.75 pi is equals to 11.78. In conclusion, in both methods, let me find out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, the area of this green semicircle equals to 11.78 square units. Okay? Thank you very much.